On July 20, 1969, Neil Armstrong and Buzz Aldrin safely descended onto the Moon in Apollo 11. It was a frightening moment with alarms firing and gas lines freezing as the astronauts barreled toward another celestial body for the first time in human history. The astronauts landed on Mare Tranquillitatis, a dark bluish plain made of ancient lava. For the next 2 hours, they explored the Moon's surface, collecting rock samples and bouncing about. It was the first of 6 more manned journeys to the Moon between 1969 and 1972. Apollo 13 was the only mission that had to be aborted, with the crew making an emergency re-entry. In 1972, Apollo 17 was the last manned expedition at a time when U.S. interest in lunar landings was fading fast. We'd been there, and now it was time for the next big space adventure. But now, half a century later, scientists have a renewed interest in what we can learn from the Moon. According to NASA, the Moon continues to be a treasure trove of science, one that might, in the future, allow for habitation. What's more, the Moon turned one side of itself away from the Earth 4.4 billion years ago and never looked back. This cosmic insult has turned the Moon's far side into a mysterious, troublesome place where, at least in the imaginations of sci-fi writers, human-hating robot aliens crashed. That it is so close yet so unexplored lends the far side of the Moon a shadowy mystique. But now, thanks to the James Webb Space Telescope, we can finally see what lies beyond the horizon, unlocking a new era of lunar exploration and discovery. Join us as we explore the mysterious realm of the Moon's dark side, uncovering obscure details and highlighting our celestial neighbor's lesser-known features. From Earth, we only ever see one lunar face because the Moon takes about the same amount of time to rotate once as it does to complete a single orbit of Earth. This is no coincidence, it's linked to our planet's strong tidal influence on our natural satellite. The result is that, more or less, we can divide the Moon into 2 hemispheres, the side that always faces us, the near side, and the one that always points away, the far side. Anyone who has gazed up at the Moon is familiar with the near side's most prominent features, many large, unruly circular dark patches against a backdrop of brighter terrain. Ancient astronomers dubbed these dark features Maria, Latin for seas, because of their water-like appearance from Earth. But they are actually plains of basaltic volcanic minerals, solidified lava that erupted out from beneath the surface long ago. The near side's brighter regions are older, heavily cratered, and more reflective highlands that rise from the plains. Astronomers had long assumed the Moon's mostly unseen face was similar, but space-age reconnaissance shattered those expectations in 1959 when the Soviet Luna 3 spacecraft beamed back the very first image of the far side. Although it was grainy and fuzzy, the photograph was still clear enough to reveal a wildly different landscape. The far side was almost all rugged highland, with the near side sprawling Maria shrunken to just a few scattered darker spots. Decades of follow-up observations only widened the shocking mismatch between the hemispheres. For instance, gravity data from the 2 lunar-orbiting Grail, Gravity Recovery and Interior Laboratory, spacecraft indicated that the far side's crust was about 20 kilometers thicker on average than that of the near side. Why were the 2 hemispheres so different? It's tempting to think Earth's tides played a role, yet nothing is ever that simple. The cause must reach back to the Moon's birth. The current origin story widely accepted by scientists is called the giant impact hypothesis, also known as the Big Splat, which I rather like. In this scenario, a Mars-sized world, which astronomers call Theia, after the Titan who was the daughter of Gaia in Greek mythology, slammed into Earth at a grazing angle shortly after our planet's formation 4.6 billion years ago. The immense release of energy tore Theia apart, sinking its core down into Earth's depths and blasting its outer layers, plus lots of terrestrial material, into orbit. All that superheated rock cooled rapidly in space and became the Moon. Scientists still argue over the details, but our satellite may have coalesced from the debris in as little as a few months to a few years. At that time, the Moon was much closer to Earth than today, perhaps only about 1/10 the current separation. Across the eons, tidal forces gradually pushed it farther out. At that close distance, the tidal interaction between the two was fierce, and the newly created Moon's rotation may have become tidally locked in as little as a year. This is far faster than the crust could have formed and solidified, which means that the hemisphere dichotomy couldn't be caused by Earth's tidal pull. Something else must have happened to thicken the far side as the crust initially cooled. However, scientists tossed around a few ideas, none proving to be perfect fits for the dichotomy we see today. Perhaps a second, smaller moon formed from the big splat's debris as well, and it eventually collided with the bigger moon at slow speed and draped the far side with more material. Maybe physical processes churning inside the newborn moon allowed one side to get thicker. Then in 2014, a team of astronomers published a new, arguably better explanation. Their culprit was not our planet's tides, but Earth itself. In all the models investigating the young moon's evolution, none had completely taken into account that Earth loomed overwhelmingly large in the lunar sky. Shortly after the moon formed, Earth was so close that it would have taken up a staggering 40 degrees of angular diameter in the sky as seen from the moon, covering a celestial area 20 times larger than it does today. Remember, at that time, Earth was hot. Thea's impact would have vaporized much of our planet's surface and melted the rest. For many centuries, if not millennia, the heat from rock boiling at about 2000 degrees Celsius would have cooked the nascent moon's near side, raising it to about 1000 degrees Celsius, while the far side would have cooled to frigid temperatures. This has profound implications. Early on, when the moon was still entirely molten, it would have had a churning atmosphere of incandescent rock and metal. Hearty elements such as calcium and aluminum have a very high boiling point and would have stayed as gas on the moon's roasting near side, whereas they would have easily condensed on the cooler far side. Those windswept elements would have interacted with others on the far side, forming relatively lightweight minerals such as feldspar, which would have floated on the surface to gradually create that side's thicker crust. Interestingly, orbital surveys do show more feldspar on the far side than on the near side. Also, this process could have concentrated other minerals on the near side, including radioactive ones that would have acted to heat the crust there and allowed magma to eventually burst forth. This would have flooded much of the near side surface to make the dark Maria while leaving the far side mostly Maria-free. So, does this solve the mysterious lunar dichotomy? It's the best idea going right now, but of course, more evidence is needed to support it. And James Webb may provide some clues. The technological achievement of NASA's time machine is uncontroversial. It's set to take the success of the Hubble a step further. What we get now is a telescope that's about 100 times more powerful than Hubble. The Webb's biggest advantage is the type of light it collects. Light comes in a lot of different varieties. The human eye can see only a narrow band known as visible light, but the universe contains lots and lots of light outside this range, including the higher frequency, higher energy forms, ultraviolet, gamma rays. Then there's the lower energy light with longer wavelengths, infrared, microwaves, radio. The Hubble Space Telescope collects visible light, ultraviolet, and a little bit of infrared. The Webb is primarily an infrared telescope, so it sees light that's in a longer wavelength than what our eyes can see. This seems nerdy and technical, but it's actually what allows Webb to look further back in time than the Hubble. Infrared light is often very old light due to a phenomenon called redshifting. When a light source is moving away from a viewer, it gets stretched out, morphing into a longer and longer wavelength, growing redder. The opposite is true as well. As a light source grows closer, the wavelengths shorten, growing blur. It's similar to what happens when a siren goes by. The pitch increases as the siren approaches, then decreases as it trails away. Because space is constantly expanding, the farthest things away from us in the universe are moving away from us. Imagine a star that's really far away. The light from that star may start off in the visible spectrum, but it gets stretched on its journey to us. It grows redder and redder. Eventually, these very distant, old galaxies grow so red that they drop into the infrared spectrum. Webb can see this ancient light that has become invisible to the human eye. Conveniently, infrared light has other uses as well. It's a really good type of light to use to look at exoplanets. For instance, if you were on a planet that orbits another star and wanted to see Earth, visible light wouldn't be your best bet. That's because the Earth peaks in the infrared. So, if we want to be able to study an Earth-like planet in another solar system, what we really want to do is observe at infrared wavelengths, because that's where the light from the Earth is being emitted. In a recent discovery, scientists have, for the first time, discovered a cave on the Moon. The inside of the cave is warmer than the rest of the Moon. The average temperature is about 17 degrees Celsius, or about 63 degrees Fahrenheit, compared to the minus 173 degrees Celsius temperature, or about minus 280 degrees Fahrenheit, which is the temperature at night. These environments could provide shelters for future human exploration of the moon. If you want to find lunar ice, you have to go to the poles. If you want to survive, you'll need access to ice for water and fuel and use the warmth of a lunar cave. And James Webb will help us identify these possible locations. So, let's hope those shadowy robot aliens have gone back to wherever it is they come from.